on the topic of causality. Our methods for comparing two samples have a powerful use in the analysis of randomized control experiments. Since the treatment and control groups are assigned randomly in such experiments, differences in their outcomes can be compared to what would happen just due to chance if the treatment had no effect at all. If the observed differences are more marked down, what we would predict as purely due to chance, we will have evidence of causation. Because of the unbiased assignment of individual to the treatment and control groups, differences in the outcomes of the two groups can be ascribed to the treatment. The key to analysis of randomized control experiments is understanding exactly how chance enters the picture. This helps us set up clear null and alternative hypotheses. Once that's done, we can simply use the method of previous sections to complete the analysis. Let's take a look at this example. Treating chronic back pain, a randomized controlled trial. Low back pain in adults can be very persistent and hard to treat. Common methods run from corticosteroids to acupuncture. A randomized controlled trial, RCT, examined the effect of using botulinum toxin A or BTA as a treatment. Botulinum toxin is a neurotoxin protein that causes the disease botulism. It's the most acutely lethal toxin known. There are 7 types of botulinum toxin. Botulinum toxin A is one of the types that can cause disease in humans, but it's also used in medicine to treat various diseases involving the muscles. The RCT, analyzed by Foster, Clapp, and Jabbari in 2001, examined it as a treatment for low back pain. They had 31 patients with low back pain, and they were randomized into treatment and control groups. 15 people in the treatment group and 16 in the control group. The control group was given normal saline, and the trials were run double blind so that none the doctors or patients knew which group they were in. After 8 weeks, 9 of 15 in the treatment group and 2 of the 16 in the control group had pain relief according to a precise definition used by the researchers. These data are in the table BTA and appear to show that the treatment has a clear benefit. So let's run the line of code and see the result in the table. You have a group and you have the result. But let's see how many patients recovered in each group. Remember that counting is the same as adding zeros and ones. The sum of ones in the control group is the number of control group patients who had pain relief. In the control group, you have 2 people. In the treatment group, you have 9 people. And again, remember that the total number of patients were 31, 15 in the treatment group, and 16 in the control group. Let's take a look at the proportion. In the treatment group, 60 of the patients had pain relief compared to only 12.5% in the control group. None of the patients suffered any side effects. So the indication are that botulinum toxin A did better than the saline, but the conclusion isn't yet slam dunk. The patients were assigned at random into 2 groups, so perhaps the difference could just be due to chance. We need to answer this question. In statistics, we usually jump into chi-square test or we build confidence interval to make the analysis. But Before doing that, let us take a look at simulation and see how we can apply the method that we just introduced in our course. To understand what this means, we have to consider the possibility that among 31 patients in the study, some were simply better able to recover than others, even without any help from the treatment. What if an unusually large proportion of such patients got assigned to the treatment group just by chance? Then, even if the treatment did nothing more than the saline in the control group, the results of the treatment group might look better than those of the control group. To account for this possibility, let's start by carefully setting up the chance model. What's a potential outcome? Before the patients are randomized into two groups, our minds imagine two possible outcomes for each patient. That patient might land in the control group, or it might be assigned to a treatment group. There are called two potential outcomes for each patient. So there are 31 potential treatment outcomes and 31 potential control outcomes. The question is about the distribution of these two sets of 31 outcomes each. Are they the same? Are they different from each other? We can't answer this question yet because we don't get to see all 31 values in each group. When we do the random assignment, we randomly select 16 of the patients for the control group and the rest, which are 15 patients, to the treatment group. Here's a good way to visualize the setting. Each patient has a two-sided ticket. Before the randomization, in the population, there is one imaginary ticket for each of the 31 patients in the experiment. So basically, when it comes to randomization, each patient's ticket looks like this. Outcome if assigned to a treatment group, and the potential outcome if assigned to a control group. After the randomization, we get to see the right half of randomly selected set of tickets and the left hand of remaining group. So basically, the data look like this. 16 randomly picked tickets show outcome if assigned to a control group, and the remaining, which is 15 tickets, outcome of assigned to treatment group. What are our hypotheses here? The question is whether the treatment does anything. In terms of the table observed underscore outcomes, the question is whether the distribution of the 31 treatment values in column 1 is different from the distribution of 31 control values in column 2. So our goal is to answer this question. Our null hypothesis says the distribution of all 31 potential treatment outcomes is the same as all 31 patients in potential control outcomes. Botulinum toxin A does nothing different than saline, then the difference in the two samples is just due to chance. Alternative hypothesis says not so much. The distribution of 31 potential treatment outcomes is different from that of the 31 control outcomes. The treatment does something different from the control. It doesn't say that it is better or worse. It just says that it is different. So remember that this is a standard in medical studies because it doesn't prejudge which way the result might go. But you are welcome to run a test for whether the treatment does better than the control. You just need to adjust your test statistic accordingly. We know that there are 31 observed outcomes jointly in the two groups. If the null hypothesis were true, it wouldn't matter which of those 31 outcomes were labeled treatment and which control. Any random subset of 16 of 31 values could be called control and the remaining 15 treatment. Now we can simulate this. We can randomly permute the 31 values, split them into two groups of 16 and 15, and see how different the distributions in the two groups are. Since the data are zeros and ones, we can just see how different the two proportions are. That's exactly what we did for A/B testing in previous section for maternal birth. Sample A is now the control group, and sample B is the treatment group. So let us go to the next line and begin the process. What is our test statistic here? If the two group proportions were very different from each other, we will lean toward the alternative hypothesis that the two underlying distributions are different from each other. So our test statistic will be distance between the two group proportions. That's the absolute value of the difference between them. Large values of test statistic will favor the alternative hypothesis over the null. Take a look at the absolute value of the difference between these two proportions is 0.475 or 47.5%. Now, if you take a look at the average, for the control, we saw that it's 12.5%, and for the treatment, it was 60%. For the observed proportion, this is what we have, 0.475. The difference between the proportions of pain relief in the treatment group and the control group is 0.475. This value represents the magnitude of the difference in treatment efficiency between the two groups. Now, as we have done before, we're going to define a function that takes the following two arguments: the name of the table of the data and the column label of the group labels, and return the distance between the two group proportions. So we define distance function, passing two arguments. The function takes two arguments, the table and the group label. The function basically selects the columns of interest. It groups the data by the group label, control, and treatment, and calculate the average of the result. This basically gives us the proportion of patients who experienced pain relief in each group. It returns the absolute value of difference between them. In our next step, we're going to simulate the null hypothesis and then compare the observed and simulated differences. Predicting the statistic under the null hypothesis. We can simulate results under the null hypothesis to see how our test statistic should come out if the null hypothesis is true. Generating one value of statistic. The simulation followed exactly the same process we used in the previous section in maternal weight. We start by randomly permuting all group labels and then attaching the shuffled label to the 0-1 results. So now we have a new column, shuffled label. And as you saw, we're simulating the null hypothesis by randomly shuffling the group labels, control, and treatment, and then calculating the test statistic based on this random assignment. This simulates what would happen if the treatment had no effect and any observed difference was due to random chance. We can now find the distance between the two proportions after the group labels have been shuffled. Let's pass in two arguments. And as you can see, the distance is now very, very small. It's about 9%. It means that the proportion of the pain relief in the shuffled groups are very similar. And as you can see, this is quite different from the distance between the two original proportions, which was about 47–48%. Now, let us set up a permutation test to simulate the null hypothesis. If we shuffled the labels again, how different would the new distance be? To answer this question, we're going to define the following function that simulates one simulated value of the distance under the hypothesis of random draws from the same underlying distribution. And then we'll collect 20,000 such simulated values in an array. You can see that we are doing exactly what we did in previous section for our permutation test. We're defining our function, one underscore simulated distance. This function generates one simulated value of the difference between two group proportions after randomly shuffling the group labels, and it takes the original labels group, shuffle them, and calculate the distance between the proportions of the shuffled groups, which basically simulates what we expect under the null hypothesis. And I'm going to repeat this 20,000 times by using a for loop. What is our conclusion here? The array distances contains 20,000 values of our test statistics simulated under the null hypothesis. Here's the empirical histogram along with the observed value of the test statistic. We can also find the p-value of the test. And remember that the large value of the distance favors the alternative hypothesis. The observed distance is 0.475. To find the empirical p-value numerically, we must find the proportion of simulated statistics that were equal to or larger than the observed statistic. And as you can see, you have your prediction under the null hypothesis, and on the horizontal line, you have the distance. And it's quite lean toward the right-hand side. So it's skewed to the right-hand side. And please pay attention to your red dot, which is representing the observed distance. If we calculate our p-value, the p-value is quite small. It's 0.009. It means that only 0.875% of the simulations under the null hypothesis produced a distance as large or larger than the observed value. Since the p-value is very small, it's less than 5%, it means that we reject the null hypothesis.